as a second example, let's go to the example of the resistors and think about this equation then that says overall resistance is resistance 1 plus resistance 2 times resistance 3 over the sum. If you think about what are partial derivatives here, well, the partial of the overall resistance with respect to resistance 1 is just 1. The partial of overall resistance with respect to resistance 2, you can do some calculus and convince yourself that this is R3 squared over R2 plus R3, the quantity squared, and the partial of overall resistance with respect to R3 is R2 squared over R2 plus R3 squared. And so then, for example, if I had, say, mean of R1 of, say, 100 ohms, with a standard deviation for R1 of 2 ohms, and both mean for R2 and mean for R3 of, for example, 200 ohms, with a standard deviation for R2 equals standard deviation for R3 of, say, 4 ohms, we might ask ourselves, well, what about a mean and a standard deviation for resistances of assemblies of this type? Well, this is not a linear function of R1, R2, and R3, but I've got the partial derivatives, and I can make use of these so-called propagation of error formulas. I can make use of these Taylor series approximation formulas and say that the mean for the overall resistance, I can't give you an exact formula, but I can say that it's approximately what I get when I plug these means into this formula. So I plug these means into the formula for R, and I get the following. I'm going to take 100 plus 200 times 200 over 200 plus 200, and when all is said and done, that's 200 ohms. And what's more, the standard deviation for R is approximately the square root of 1 squared times 2 squared. Okay, this is the partial with respect to R1. This is the square of the standard deviation for R1, plus 1/4 squared times 4 squared, and this is the partial with respect to R2 evaluated at the mean values for R1, R2, and R3, times the variance for R2, and then the corresponding thing is 1/4 squared times 4 squared for the term coming from resistor 3. When all is said and done, that is 2.45 ohms. And the beauty of this is I've got a way of arguing that says that if I have this kind of variability on the inputs, I've got a reasonable handle on what kind of variability I can expect on the output of this system by making use of these partial derivatives and variances. Those are analytic pencil and paper calculus kinds of tools. Of course, for complicated problems, you might use something like MathCAD or Mathematica to do these computations. What I need is partial derivatives squared times variances added up to get a variance.